most people said they're already familiar with the concept of the equilibrium constant. Okay? The notation we'll use is K sub EQ. It's a relationship between the concentrations of products and reactants in a simple reaction at equilibrium, okay? Or it describes the composition of your system once equilibrium is reached, right? Keeping in mind that equilibrium is once sufficient time has passed. Keeping in mind that this reaction is a reflection of there's both a forward direction and a reverse direction, and so if we wait a long enough amount of time, how much products and reactants do we expect to be there? So here's our sort of simple reaction case we have. Our lowercase letters here are our stoichiometric coefficients to make things balanced, right? Okay, so we have A and B reacting to make C and D, with these lowercase letters being our stoichiometric coefficients to keep things balanced. This particular figure, which I grabbed from the internet, has C for the equilibrium constant. I use KEQ on your equation sheet. The equilibrium constant is given by the concentrations of the products at equilibrium. So once equilibrium is reached, the concentration of product C, or take them, product across all the products, concentration of C raised to the stoichiometric coefficient for C, okay, times the concentration of D raised to the stoichiometric coefficient of D. Okay. If you had some third product over here, E, okay, that would also be on the top, right? So you have for the forward reaction, these are your forward products raised to their stoichiometric coefficients divided by the forward reactants raised to the reactants coefficients. And so the equilibrium constant for the reverse reaction then is one thing you can do, if it's easier for you, rewrite the entire equation so that C plus D are now on the reactant side, draw your arrow pointing to the right, and put A plus B on the other side if that's easier for you to think about, okay? Right, but for the reverse direction, these are now my products. Products are on the top, reactants are on the bottom, but for the reverse reaction, it would just be 1 over the equilibrium constant to get that value. So here was our ATP hydrolysis reaction. Okay. ATP being hydrolyzed to produce ADP and a phosphate ion, so we could write our equilibrium constant as the concentration of our products. This is for the forward reaction is how this is written. ADP, concentration of ADP times the concentration of phosphate ions. These are both technically raised to the 1, okay? But there's no, I haven't written a 1 for my stoichiometric coefficient here. ATP is my reactant, it's on the bottom. What is my other reactant here? Why isn't it shown? So remember this real reaction, there's water on the left-hand side for the forward reaction, hydrolyzing ATP to make ADP. So the equilibrium constant, the real full-on version of the equilibrium constant actually looks like this. I have the concentration of ADP at equilibrium divided by the concentration of standard state ADP. The standard state ADP is 1 molar by definition, so it's just not there, okay? And this is phosphate ions at equilibrium divided by phosphate ions, the standard state concentration. Okay? And on the bottom, same thing. The real term is ATP over standard state ATP. And for water, it's the concentration of water divided by the standard state concentration of water. This is 1 molar. This is 1 molar. This is 1 molar. This is 55 molar over 55 molar. Okay. There's so much excess water that the concentration before and after the reaction remains approximately 55 because everybody else that's reacting is in the millimolar range. It's basically not affecting the concentration of water. So the concentration of water and the standard state concentration are both 55, then this is just equal to a 1, so I don't need that term at all. That's where it went. Okay, so what we're going to do next is derive the relationship between KEQ and free energy change at standard state, and then we'll take a break.